Hi guys, and welcome to my channel. Today I'm going to be doing a COMSOL tutorial on chemical etching or wet etch used in the micro patterning of ICs, integrated circuits, and MEMS devices. I think MEMS is micro electronic memory devices. I can't remember the acronym, but two types of semiconductor devices. And as opposed to dry etching, this uses a solution-based wet etch. So like it sounds, it's wet because you have a solution and it's immersion into a tank of some chemical solution, depending on your target and your desired outcome. So the wet etching comprises 3 steps: transport of the liquid etchant to the substrate, a redox reaction followed by dissolution, and then transport of the byproducts in the reaction. So your standard transport phenomena here. Here's the 2D geometry that we'll be working with. So we have a block representing the laminar flow for the etchant with a mask on bottom, and then a deforming boundary with the etching copper substrate. So here we have linear kinetics at flow at the reacting interface here, and laminar flow on the bulk flow portion of the model. And then we'll be using 2 physics from the COMSOL multiphysics package: transport of dilute species and laminar flow, SPF, single phase flow. Right, and then we'll also be using a deforming boundary in the geometry. So here's some of the results that we'll talk about at the end. With our concentration profile, you can see the boundary, the deforming boundary changed from this to a bird beak looking profile. And then our velocity profile, you see a much higher velocity profile in the bulk than you do in the small ED filling the cavity, which makes sense. Okay, the normal mesh, this is just pointing out that you have more elongated triangle mesh elements inside the cavity, and the mesh dynamics vary largely where fluid can access the cavity. So you see the mesh elements in the bulk flow and along the outside of the deformed boundary part of the model are more like equilateral triangles, and in the center where it's most deformed you have the most elongated mesh elements, and then compressed mesh elements can see near the bottom domain. Alright, and then our results, we'll look at that once we do the model. Okay, so this is the chemical etching model in the COMSOL multiphysics application library, which will be linked in the description of this video. Okay, so here are our target, or our substrate actually is an unmasked copper. I thought we were using a semiconductor substrate like silicon, but we're using copper for this etching process. So we're etching a metal here. So we've got copper. This could be, I don't know, metal on top of a via or something. So we're etching away part of the metal. And here are the governing equations. So we've got our governing equation for transport of a chemical species, partial differential of concentration with respect to time, plus u, the velocity vector. So this would have an x, y, and z component, and that's multiplied times del concentration, again with respect to x, y, and z, equals del times d, large D, the diffusion coefficient, times del C, the concentration of the reacting species. And then we also have the flux condition for the moving boundary. So d diffusion coefficient, times del concentration, times n, the normal vector, equals negative k, the etching rate constant for linear kinetics of the etching species, times c, the concentration. And then a no flux condition will be used for all other boundaries except the moving boundary. Our governing equation for laminar flow is the Navier-Stokes equation, where the differential of the velocity vector with respect to time equals the combination of a Okay, so the different terms, Navier-Stokes equation takes into account different forces. So this term takes into account the pressure forces. This is our negative P term. No, I can't just highlight that. That's our negative pressure forces. We've got viscous forces in this term, and then our body force term, so the external force applied to the fluid, so that would probably just be gravity? I don't know. Okay, and then this is solved along with our mass continuity equation. So we've got del U equals 0. The full continuity equation is this, so partial differential of the fluid density with respect to time plus the total differential of the fluid density times the velocity vector equals 0, which can be simplified to just del U equals 0, which gets rid of our identity vector term here, and then also these terms. So we're left with a much simplified equation. And then along the moving wall, we have a no-slip condition applied. We're also going to use a deform geometry boundary, since the movement of the boundary is defined by an interfacial condition on the boundary. So we'll have v, the velocity of the moving mesh in the normal direction, equals dm over rho. So the diffusion coefficient times the molar mass over the density of the etching species. Alright, and we'll look at the results. So, to get started, let's do a model wizard. And also the application library path is under COMSOL Multiphysics, Chemical Engineering / Chemical Etching. So we're going to do a 2D model. For physics, we're going to expand chemical species transport and select transport of dilute species and add. And then we're also going to go under fluid flow, single phase flow, and choose laminar flow, and also click add, and then study. We're going to do a stationary study here, and click done. So let me save this as chemical etching. Save chemical etching. Okay, so we're going to start with global definitions. In the model builder window, expand component 1 definitions node, and then we're going to click global definitions parameters 1 and load from files. So your little folder icon down here. And as always, I've saved the text file beforehand, so you can get this from the link in the description and just save the text file here. So we've got all these parameters, the bulk concentration of copper chlorate, Cooper's chlorate, I don't know how you would say that. Copper chloride. Alright, so the bulk concentration of our etchant species, copper chloride, KF, or the forward rate constant, MCU, the molar mass of copper, rho, Cu, the density of our etchant species, the height of the mask, the seed cavity height, the mask length, the boundary layer width, and the diffusion coefficient of the reactant species. Alright, so there's all of our parameters. Now we are going to create definitions. So any function definitions or variable definitions. So we've got a couple variables to add here. In the home toolbar, click on the variables, the A equals icon, and then we're going to choose which one do I go at? Oh no, it's saying in the model builder window under component 1, right click definitions. So these are going to be local variables, and choose variables. So just to talk a second about scope of variables, you can add variables here. So there I added local variables, and you see it appeared under component 1. I'm going to delete this because I don't actually need it. But if you wanted global variables, it would appear under the root node. So you can see if you collapse component 1, it's actually a subnode of the root node, chemical etching, the file name. So global definitions are going to apply to any node, any subnode in the root node. So if I defined global variables, that would apply to component 1 and any additional components I might create, component 2 through 10. But in this case, we are creating local variables. So the scope of that variable only applies to component 1. In this case, I don't know that it matters because we only have one component, I think. But just to be mindful, if you have a global variable of the same name, it will override any local variables. And I don't even know, COMSOL might not allow you to do that. I've never tried. So we're going to create these local variables in this table. V surface will be the expression -r underscore surface times the molar mass of the etchant species over the density rho of the species. Alright, and it's in yellow because it's not recognizing our surface. Oh, because we haven't defined it yet. It's the next one. So this is the surface normal velocity, and then our next variable is going to be our surface. So -kf, or the rate constant in the forward direction, times concentration of copper chloride, CuCl2. And let's see, unknown variable C. Okay, so we have a parameter called CuCl2 Bulk, but that's hard, that's a mouthful. CuCl2 is going to be a function of the TDS physics, so we'll actually be solving for that, right? The concentration of copper chloride in the domain. So that's why that's yellow. Why is this still yellow? Oh, okay. So now it's referencing this, but it's still yellow because there's an unknown in our surface. So once it actually solves for TDS, then that will clear up. Okay, so we're ready for geometry. Let's go to geometry toolbar, and we're going to add a rectangle since we're doing a 2D geometry. Locate the size and shape. So for the width, this rectangle is going to have a width of dmask, or the width of the mask, and then a height of H mask, the height of the mask. We're going to add a second rectangle. And the width of this one will be H boundary layer, the width of the boundary layer, and the height will be H seed cavity. Okay, and then for the position, the X coordinate will be negative H seed cavity, and the Y position will be negative H seed cavity. Alright, and then we're going to build a fillet. So in the geometry toolbar, click the fillet option. So it's a dotted line square with a curved arc across the center of the square. And click the zoom extents button. So we have a more appropriate scaling for our field of view here. And then we're going to click on R2. Oh, that's rectangle 1. Select point 1 and 2 only. So this is rectangle 2 on bottom, and we want points 1 and 2 only, which are the bottom, left, and right hand points of that bottom rectangle. In the settings window for fillet, locate the radius section. And in the radius, we're going to type value H seed cavity over 2. Now we're adding a third rectangle. So by hitting the third geometry, it already executed that fillet, so you can see it just took off the edges of the bottom rectangle. Alright, so for the width of our third rectangle, it's going to have a width of D mask times 2, and the height will be 3 times height of the mask. And then for the position, we're going to have an X coordinate of negative D mask over 2 and a Y coordinate of H mask for the base corner. And build all objects. I'm going to hit zoom extents again so we can see the whole view. So here's our bulk flow of the etchant species, or deforming boundary, and then the top side of this at this interface is the copper substrate. Alright, now for our moving boundary definition. So in the definitions toolbar at the top, the second one next to home, we're going to click on explicit. So this top icon in this section, and in the label text field we're going to put moving boundary. And then we've got to select the boundaries. So, I've got domain here. So we've got to change from boundary, or from domain to boundary, and then we're going to choose everything on that moving boundary. Nope, not that one. I have to zoom in here. Alright, so we're picking 4, 6, 13, 16, 15, and 16. Now we're ready to add the material, or component. So we're going to click Add Material from the Home toolbar, which opens up our library, and then we're going to go to Built-in and search water. Water liquid. Alright, there we go. So we'll add the component and close out of this material library and move on to our physics definitions. So now we're ready for boundary conditions and initial conditions. So we're going to do transport of dilute species and then laminar flow before we go to the mesh define. Before we define the mesh. So for transport of dilute species, we're going to expand that and click on Transport Properties 1 and locate the convection section. Okay, so for U, the velocity field, we're going to change this from user-defined to velocity field SPF. And in the diffusion section for D, the diffusion coefficient, we're just going to put D, so it references our variable. For concentration, we're going to expand component 1 transported to least nodes. We're going to click on no flux 1 node. Right click on transport of dilute species and choose concentration. So that adds another boundary condition. Select boundaries 1 and 3. Okay, so boundary 1 is the left-hand side where bulk flow of etchant is entering, and boundary 3 is the top of our bulk flow. In the settings window for concentration, locate concentration section. So we're going to select the species C, and in the C0 text field, we're going to put CuCl2 Bulk. So that was in our global definition of a parameter. Okay, so at the beginning I should have done this. You can change the dependent variable. Default is just C for concentration, but you can actually put in a specific species here. So I should have done that at the model beginning. There we go. Oh, no. Remove. Okay, so that changes our default value here to C0 of concentration, CuCl2. Alright, now we're going to add an outflow condition by going to the physics toolbar, clicking on boundaries, and selecting outflow. And selecting boundary 14. So here's where our etchant is coming out, it's traveling from left to right. That's it for outflow. Now we need to add a flux condition. So physics, boundaries, flux, and then from the selection, we're going to choose moving boundary, which we already defined as the bottom here, and locate the inward flux section at the bottom. Select species, concentration of copper chloride, and in the section for the flux vector, J, we're going to type our surface, which we defined previously as the reaction rate at the surface under the local variables. Okay, now we're ready for laminar flow. So in the model builder window, click on laminar flow SPF, and in the physics toolbar, click boundaries and choose wall. So we're adding a wall. Oh, we already had a wall condition. Okay, so select boundary 3 only. That's our top wall, and from wall movement, we're going to expand this section. Okay, so after expanding the wall movement section, we're going to choose manual from translational velocity list. And then specify the velocity vector as an x component of 1 millimeter per second, and the y component is 0. So it's only moving in the x direction at this speed. Now for adding the boundary stress condition, we're going to click on physics, boundaries, and boundary stress. Here it is, under laminar flow. And select boundaries 1 and 14 only. So 1 is the entrance, 14 is the exit. Alright, component 1. So we're going to add a Deform Geometry component, or Deform Geometry 2 component. In the Definitions toolbar, click Deformed Geometry. Let's see. Where is it? Oh, off to the right under Moving Mesh, we have the Deform Geometry. It's like 2 rectangles icon. And choose Domains, Deforming Domain. Alright, and then we're going to select Domain 2, the one with the moving boundary on bottom only. In the Settings window for Deforming Domain, locate the Smoothing section. From the Mesh Smoothing type, choose Hyperelastic. So we've got to choose from Laplace, Winslow, Yo, and Hyperelastic. Okay, prescribed normal mesh velocity 1. In the Definitions toolbar, click Deform Geometry and choose Boundaries, Prescribed Normal Mesh Velocity. So we see a new subnode appear under Deforming Domain 1. And then in the settings for this new node, locate the boundary selection section. So we're going to change this to moving boundary. Alright, and then under the prescribed normal mesh velocity section for Vn, the normal mesh velocity vector, we're going to type V surface. And this again this will reference our definition for the variable in the local variable section. Alright, now we're going to add a mesh displacement boundary. So again, Deform Geometry from the Definitions tab and choose Boundaries, Prescribed Normal Mesh Displacement. We added a normal mesh displacement at boundaries 5 and 11 and a prescribed mesh displacement at boundary 8. Alright, so let's try this again. Try to pin it. Compute. So here's our surface profile. And then we're going to look at the arrow surface. So right click Velocity and choose Arrow Surface. And then we're going to go to Coloring and Style, change arrow length to logarithmic, and make the color white. And then click Plot. So just to better see the magnitude of our velocity field, we've got a very high velocity at the top of the bulk flow and then very low velocity in the eddy flow within the moving boundary, or the deforming boundary. Alright, and then for the pressure plot, it's a contour plot instead of a surface plot. We're going to hit Zoom Extents, it says, and then under Results, click Pressure SPF, and toolbar click Plot. Well, it was already plotted, so we didn't need to do that. Alright, so we're going to add a plot group from Mesh. So in the Home toolbar, click Add Plot Group. And we're going to add a 2D plot group. So we're going to put Mesh in the text label field here. Okay. And then right click Mesh and choose Mesh. So from the different types of 2D plot groups we have, we can do a line, contour, streamline. We're going to add a mesh plot. And then click Plot. So this is just showing our mesh deformation. So you can see light green is a value of 1, and 0 is a value of red. So we've got, okay, so you see more elongation and just variation in general from element to neighboring elements in the areas where this deformation is occurring and where the etchant is able to enter the cavity. Alright, and then we can do a little animation here by going to Results, Animation, Player, or if you want to save it, you can do it to File instead of Player, but we'll just play it inside the GUI here. And then for the settings for animation, we'll go to Frames, Show Frame. Let's do a zoom extents here so we can see the whole model. And then we're going to choose all frames from the frame selection list. And then in the frame number, we'll put 101 and click play. So we're going to watch 101 frames of the progression. So you can see as the deformation occurs, let's play it again. So from that animation, we can see depletion at the outflow. We can also see that the etchant flow affects the symmetry of the etching process, which is well known for wet etching. You're not going to have very good uniformity. If you required high uniformity, then you would probably be using a dry etch instead of wet etch. And also you see the uniform concentration near the moving boundary with increased aspect ratio. Right, so our depletion at the exit of the bulk flow, you can see by the lighter red here as compared to the concentrated crimson color across the region at the entrance. It sort of tapers off. And then the aspect ratio, uniform concentration near the moving boundary with increased aspect ratio. So just pointing out that this moving boundary, the dark blue at the bottom of the moving boundary for the deformation region, stays uniform, but this cavity within the deformed boundary area has an increased aspect ratio, meaning the height to the width increases with time. So the width's going to stay about the same, but you've got an increased aspect ratio of non-uniformity as the etch progresses. And the other thing to keep in mind is that because it's an exothermic reaction, you have increased temperature in the bath. So you can imagine, since this is a wet etch, you've got your substrate with your metal layer on top here that you're etching, and the whole bath is getting exposed to the exothermic reaction, so the whole bath is increasing in temperature, which impacts the reaction rate as it progresses. And if it becomes too hot, then you're going to have even more non-uniform etch and uncontrolled process, and also it could become dangerous. So that's just more context about what's going on outside of this very local process we're modeling. Okay, so that was it. If you enjoyed this tutorial and you want to see more COMSOL tutorials, please like, comment, and subscribe, and I'll see you in the next video.